The photoelectric effect was a cool experiment that verified Planck's work on early quantum, that the energy delivered by light comes in little bundles called photons. Einstein won a Nobel Prize for it. The math on it's kind of cool and kind of simple. If you shine light at a metal, the energy of the light, according to Planck, energy of light follows E equals h times f, where f is the frequency of the light source. If we apply the universal wave equation, f is the same as speed over wavelength. Speed of a light particle being the speed of light, our equation for the energy of light is hc over lambda. If we shine light with enough energy on a metal, as long as the light's got more energy than what we call the work function of the metal, the work function is sort of the base or the threshold energy that we have to beat. If the light doesn't have enough energy, if the energy of the light isn't greater than the work function, no electrons will get released. But if the energy of the light is greater than the work function, then we'll get electrons ejected. The electrons will have kinetic energy. The kinetic energy that the electrons have, we usually figure out by using a parallel plate apparatus and applying a voltage. The greater the negative voltage, to stop the electrons, the greater the kinetic energy the electrons must have had. So the kinetic energy of the ejected electrons is their charge multiplied by the voltage it takes to stop them. The energy of the light is related to the frequency or wavelength, and as long as the energy of the light is greater than the work function, then electrons will be ejected. Let's look at some actual numbers. Light shines on a metal, electrons are ejected. Those electrons are stopped by a particular voltage. There's enough there that we can figure out the work function. First, we can figure out the energy of the light. Planck said, energy of light was always h times f. Because of the universal wave equation, that's the same as hc over lambda. H is Planck's constant. It has a value of roughly 6.63 times 10 to the negative 34. The speed of light is 3 times 10 to the 8. The wavelength of the light being used is 497 nanometers, or 4.97 times 10 to the negative 7 meters. If we crank all that out, the energy of the light works out to be 4 times 10 to the negative 19 joules. Each little machine gun bullet of that light carries 4 times 10 to the negative 19 joules of energy. Next, the question says that they're stopped by 0.5 volts. The voltage it takes to stop them is related to the kinetic energy they have. So we can say the kinetic energy they carried, and that's the maximum kinetic energy. There might be some with less. The kinetic energy they carried is their charge multiplied by the voltage to stop. The charge on an electron is 1.6 times 10 to the negative 19. The volts to stop was half a volt. If we multiply that out, I'm going to put it in kind of funny notation, 0.8 times 10 to the negative 19 joules. So really what we've just figured out is that if we shine the light arrives with an energy of 4 times 10 to the negative 19. That's enough energy to kick out electrons, but the electrons only leave with 0.8 times 10 to the negative 18 joules of energy. If we think about Planck's original equation, the kinetic energy, the maximum kinetic energy of those electrons is the difference between the energy of the light and the work function. We just figured out that the kinetic energy was that 0.8 times 10 to the negative 19. The energy of the light was at 4 times 10 to the negative 19. And that's after we subtract off the work function. If you do a little bit of math on that, flip-flop things around, the work function ends up being 3.2 times 10 to the negative 19 when we're in joules. Often work functions are given in electron volts. The conversion factor to go from a joule to an electron volt is to divide by the charge on the electron. So this one works out to be nice numbers that the work function is approximately 2 electron volts.